Hello, this is part 2 of a two-part series. I suggest you watch part 1 linked in the description to understand the derivation of this formula. Well, let's jump into the video then. So if we look at our formula, it looks fairly strange, but if we graph it with respect to s, the changing number of sides, it looks even stranger, especially between -2 and 2, but for now let's ignore that region. If we look at the graph when s is large, it looks oddly parabolic, and if we compare the graph to a parabola, they follow almost the same path. So what if they are connected in some way? Maybe we can express the outer portion as a parabola. To figure this out, we are going to start off with some very basic calculus and then go into some talk about series. The first thing we need to look at is the basics of derivatives. The derivative of a function gives us its slope at every point, and for a function f of x, its derivative is f prime of x. Let's look at x squared as an example. Its derivative is 2x, which means if we go to x equals 3, it tells us the slope at x equals 3 for x squared is 6, which if we graph, yes, that is correct. Now, if we want to find a derivative, it can be fairly complicated for many functions, but thankfully for any function of the form c times x to the n, it's easy. Its derivative is n times c times x to the power of n minus 1. So for example, 2x cubed, n equals 3 and c equals 2, which means its derivative is 2 times 3 times x to the power of 3 minus 1, or 6x squared. Now, if we have multiple terms summed together, the derivative is just the sum of the derivative of each term. For example, x squared plus x's derivative is just 2x plus 1, the derivative of each term added. And lastly, the derivative of a constant like 1 or 29 is just 0, as a straight horizontal line has no slope. With the derivative of a function, we can create a thing called a Taylor series, which is a representation of the function. How this works is we take the value of the function at 0, and we add that to the value of the derivative at x equals 0 times x, and then the second derivative divided by 2 times x squared, and so on following this formula. For example, if our function f of x looks like this, f of 0 equals 1, f prime of 0 equals 3, f double prime of 0 equals 2, and f triple prime of 0 equals 12, and so on, we can assemble this function, 1 plus 3x plus x squared plus 2x cubed, and so on, which represents f of x as when we evaluate it and its derivative at 0, it has the same derivatives. So now let's try with a real function, let's say cosine, which bobs up and down. Its derivative is minus sine and its second derivative is minus cosine, and then sine before its derivative returns to cosine. If we get its first, second, third derivatives all the way up to infinity, we get 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, and so on, taking its derivative at x equals 0. If we assemble this into our polynomial, we get cosine of x is equal to 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6 plus 1 over 8 factorial x to the 8, and so on, with the more terms we add, making it a better approximation for cos x. Now we can get back to our actual task and see what's going on with our polygon function, and why it looks so much like a parabola. We can just take the Taylor series of cot and see what it behaves like, but we encounter a problem because cot 0 is undefined, so we are going to have to take another approach. Thankfully, if a function is equal to an operation between two other functions that have a Taylor series, we can just use the operation on the Taylor series to get the Taylor series of our function. Now let's look back at cot. It can be written as cosine over sine, which both have Taylor series, cosines being the same as earlier, and sines being x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7 plus 1 over 9 factorial x to the 9, and so on. But now the question becomes, how do you divide an infinitely long series by another infinitely long series? Well, we just use normal long division, as if this were a polynomial being divided by another regular polynomial. Finally, we get that cot x equals 1 over x minus x over 3 minus x cubed over 45 minus 2x to the 5 over 945 minus x to the 7 over 4725, and so on, which has a different name and is called a Laurent series, which just means it has a negative power as opposed to a Taylor series, which only has positive powers. Now we can see what cot pi over s looks like as a polynomial. If we sub pi over s into the cot Laurent series, we will get s over pi minus pi over 3s minus pi cubed over 45s cubed minus 2 times pi to the 5 divided by 945 times s to the 5 minus pi to the 7 divided by 4725 s to the 7, and on and on. But remember, our formula has s times cot pi over s, so we have to multiply everything by s, so every term gets one more s power, and we get s squared over pi minus pi over 3 minus pi cubed over 45s squared minus 2 pi to the 5 divided by 945s to the 4 minus pi to the 7 over 4725s to the 6, on and on. Now, as s tends up to infinity, corresponding to a shape having more and more sides, all the terms past pi over 3 tend to 0. For example, the term pi cubed over 45s squared, which for s equals 10 already equals 0.00689, compared to the main terms like s squared over pi, which equal 31.83, which is far more significant to the total. Meaning that for an approximation we can ignore them as they quickly become negligible, leaving us with s times cot pi over s roughly equaling s squared over pi minus pi over 3, which we sub into our formula to get the approximation to be a equals L squared over 4 times S squared over pi minus pi over 3. Now let's check this. On the graph, you can see the red line, our approximation quickly becomes very accurate. Let's try it out on a decagon with 4 cm sides. Our original formula gives 123.107 centimeters squared, while our approximation gives 123.135 centimeters squared, only 0.023% off. Pretty good, I'd say, and it only gets more accurate as s increases. Thank you for watching my video. I hope you enjoyed the video and learned something new. Please like and subscribe. Thank you, and have a nice day.